You have probably used a thermometer in a kitchen, outside a window, or under your tongue, and watched a number settle into place, as if the device is directly reading heat. Most people assume a thermometer simply detects temperature, the way a camera detects light, as if temperature is a thing you can sense directly and convert into a number. But that assumption is incomplete, because a thermometer does not measure temperature by touching temperature itself. It measures some physical property that changes in a predictable way when the thermometer and the object reach the same temperature. What exactly is changing inside the thermometer? How does it turn that change into a number you can trust? And why does it sometimes take time or give different readings depending on where you place it? This will be clear once you see a thermometer as two parts: a sensor that changes with temperature, and a scale, or electronics, that translates that change into a temperature value. The main misconception to correct early is the idea that a thermometer measures temperature instantly and directly. In reality, a thermometer has to exchange heat with what it is measuring. If you put a thermometer into a cup of tea, heat flows from the tea into the thermometer until they reach thermal equilibrium, meaning they settle at the same temperature. Only then is the reading meaningful. If you move the thermometer too soon, it is still partly at its old temperature, and the number is a compromise between the thermometer's previous state and the tea's actual temperature. This is why wait for the reading to stabilize is not a formality. It is the basic physics of measurement. From there, most thermometers work by choosing one physical change that is smooth, repeatable, and easy to interpret. The classic example is the liquid and glass thermometer. You have a bulb at the bottom and a very thin tube above it, called a capillary. The bulb contains a liquid, often mercury in older designs, or alcohol in many modern ones. When the temperature rises, the liquid expands, meaning its volume increases slightly. Because the capillary tube is very narrow, that small increase in volume forces the liquid to move noticeably upward as a column. When the temperature falls, the liquid contracts, and the column drops. The cause is thermal expansion. The process is liquid volume change, constrained into a thin tube, and the result is a visible height that can be read against a calibrated scale. A detail that matters, and often gets missed, is that the thermometer is designed to amplify a tiny physical change. Liquids expand only a little per degree, so the bulb is made relatively large, and the tube is made extremely thin. That way, a small volume change produces a large change in height. This is also why these thermometers have a limited range and sensitivity trade-off. If the tube is too thin and the bulb too large, the column might run out of space at high temperatures. If the tube is wider, the changes become harder to read. If you want a visual reference for what bulb plus capillary plus scale looks like in practice, a close-up diagram of a liquid and glass thermometer makes the design logic easy to see. Many everyday thermometers today are digital, and the misconception shifts. People assume digital means it measures temperature in a completely different, more direct way. But the principle is the same. Measure a predictable change, then translate it. In many digital thermometers, the sensor is a thermistor, which is a resistor whose electrical resistance changes with temperature. Typically, an NTC thermistor has higher resistance when it is cold and lower resistance when it is warm. the thermometer's electronics sends a tiny current through the thermistor, measures the voltage response, and uses a stored calibration curve to convert resistance into a temperature number. The cause is temperature-dependent electrical behavior in the material. The process is measuring resistance electronically, and the result is a temperature displayed on a screen. A practical implication follows from this mechanism. If a thermistor is not in good thermal contact with what you are measuring, it will mostly read its own temperature, which may be influenced by air gaps, insulation, or even your hand warming the probe handle. That is why probe placement matters in cooking, and why clinical thermometers are designed to press the sensor into contact with tissue and to reduce the influence of surrounding air. Digital does not remove the need for equilibrium. It often just makes the sensing faster and the reading easier. For a visual sense of the kinds of devices that use thermistor probes, product photos of thermistor thermometers show the typical layout: a probe containing the sensor and a display unit that performs the conversion. There is also a family of purely mechanical thermometers, often seen in ovens or outdoor dials, built around a bimetallic strip. This strip is made by bonding two metals together that expand by different amounts when heated. When the temperature changes, one layer wants to lengthen more than the other, so the strip bends. In many dial thermometers, the strip is formed into a coil or spiral. As it bends, it produces a rotation that moves a pointer across a scale. The cause is unequal thermal expansion of two bonded metals. The process is bending translated into rotation, and the result is a readable needle position. This helps clear up another misconception, that thermometers are supposed to agree in every situation. Different thermometer types respond differently to airflow, surface contact, and rapid temperature changes because their sensors have different thermal mass and different exposure to the environment. A liquid and glass thermometer has glass and liquid that must warm together, so it may respond more slowly. A small thermistor can respond faster, but can be influenced by tiny drafts or poor contact. A bimetal dial is robust, but can lag and may be less precise for small changes. None of that means one is fake. It means each one is optimized for a certain use case. Historically, the reason these systems became standard is simple. Once you can find a physical property that changes smoothly with temperature, you can build a repeatable measurement system by calibrating it to fixed reference points. In everyday terms, you anchor a scale to known temperatures, and then the thermometer's internal change can be mapped to intermediate values. That is the quiet reason thermometers are trustworthy, not because they sense temperature directly, but because their behavior is stable and their scale is tied to agreed references. So the central idea is calm and straightforward. A thermometer measures temperature by letting a sensor reach the same temperature as what it touches, then reading a physical change that reliably tracks that temperature, such as liquid expansion, electrical resistance change, or metal bending. The number you see is the final translation step, not the raw measurement itself. This understanding matters in everyday life because it explains why waiting a few seconds can change a reading, why placement and contact matter, and why different thermometers can disagree briefly before settling. When you treat thermometers as heat exchange instruments rather than instant truth machines, you naturally use them in a way that produces more reliable results, whether you are checking a fever, cooking safely, or comparing indoor and outdoor conditions.